Welcome to another GCBASIC tutorial demonstration. This is part 17. We're looking at the GCBASIC toolchain. And this particular discussion fits all the legacy chips of 10Fs and 12Fs. You just generalize what I'm saying, and it applies. But this is a discussion about the toolchain, not specifically programming. So please like and subscribe this video. If you subscribe to the channel, you'll get the latest updates, and let the video run all the way through. Thank you. Part 17, toolchain. 2 more to go. This is not a very technical discussion, but I find a lot of people don't understand the sheer amount of tools in the toolchain that you can take advantage of, and this is addressing that need. So you've already sort of hopefully understood that GCBASIC is a compiler. It does this particular PIC, it does many AVRs, LGTs, about 1,500 different microcontrollers, and it supports this particular 16F chip family. You've seen all that. But the toolchain is extensive. I'm going to zoom in, I think, on that, and we'll sort of look around and see what we've got. We've got the compiler at the top. That's the thing that takes your source code and actually turns it into a hexadecimal file. We used to have, and still have, an older version of a thing called Great Cow Graphical IDE. Well, you'll see in 2025 that's been replaced by a better tool. But that allows you to do drag and drop of simple blocks of code. There's a tool called AVR-Info, which is actually a code generator that allows you to examine the characteristics of AVR chips. Just go function key F4, AVR-Info, and it's there. We've been looking at PICINFO. We also include the programming tools called AVR-Dude, because if you're using an AVR, you need it. There's a CLC designer, and it's a Windows version, so you don't have to use Microchip's MPLAB. Lots of converters. We've seen converters in one of the demonstrations. You can write your own converters. There are many included. Cool terminal, and there's another terminal already included. And there's bootloader programs like DFU bootloader. But then there's two very important pieces. There's GC Studio. I'll pick up my pen. I'm going to get rid of my pen there. I'll just erase that because my pen's not in the right place. Erase. There's GC Studio. That is the management tool for the whole environment. Think of it as being our integrated development environment, but it will automatically update your system. Don't avoid it, because your system will get out of date extremely quickly. We release it every month, every 3 months, when the major changes come through. GC Studio is the entrance point to all these tools. Then you've been seeing GC Code. GC Code is the editor or IDE, and you can access many of the tools that we're discussing here through the function key F4. Just press function key F4 and they're listed. GS tool, we used to have an older version. And some people still may be using that, but it manages the older editor. And then there's a whole series of programmers. We have the K50 included, Micronucleus, Northern Software. Wow, we got all integrated, and you can use those. PICINFO, we've seen that. It gives you information around the chips you're using. You get PICKit2 included. You're going to get a new version of PICKit in 2025. I'll provide a free version of PICKit Plus very soon. So all this will be replaced by a brand new tools, and it will support all the legacy chips, just as this does, but it's going to be all updated for Windows 10 and Windows 11 and Windows 12. If you have PICKit Plus, you can integrate it with great ease. It just plugs in. Then there are more programmers. Another programmer, PICPGM, very old programmer. Then we have PPS tool, and we haven't been using PPS tool, but PPS tool is important if you have PPS, but the legacy chips don't. We have the program editor, and we're going to look at that in particular. There are some design tools like PSMC, which is a designer. You've got a terminal in PuTTY. You've got the older legacy Synwrite IDE, still there, still supported. Terminal software, which you've seen. And then you've got other programmers like the bootloaders. You've got express loaders. And you've got MP Labs integrated. If you install that, it will get integrated into the environment. So you don't have to go outside of the IDE to make it work. Then you've got a thing called, you might hear me talk about a thing called GCASM. It's not a standalone application, but it's the linker that's built inside of GCBASIC. And then we integrate with and work with PICAS, MPASM, and GPASM, all different types of linkers. It's a huge amount of software installed, and it all works. It's tested, and we try to keep it up to date the best we can. Big list, worthwhile having a look around the different tools if you want to use them. We're going to use some of those tools. We're going to use PICAS in the next training video, the next tutorial. We're going to use a bit of MP Lab because you need to see them working. So we spoke about the window IDEs. Let's look at a quick video here because it's worth seeing this video. I need to get rid of the point. I need to go back to my pointer here. Okay. I'm opening up GCBASIC, the actual website, and it's worthwhile seeing this video. It's not a video, it's live. Well, it tells you a little bit about the video here, but there's a video further down, which is the different IDEs we have. Like Jekyll and Hyde, all things comes in twos. What a great statement by Angel there. Okay, Angel is the main developer of this fantastic website. So on the left, you've got the IDE that I've been using. You'll go, no, it isn't. I'll show you in a minute. It is the same one. But if you want to use the old legacy one, you can just select it and select legacy mode. And it was legacy in terms of the IDE, not the chip supported. The chip supported with the new IDE are the same as with the old one. In fact, if you look at that, it's the same code. Just brilliant. So we support 2 different editors or IDEs. Around there, we have programmers. We've seen some of the programmers on the big list, and we have GC Studio managing the whole environment. Then we have Program Editor, and we'll look at that, and it's the Preferences Editor. We'll look at that shortly. PPS tool, you might need that. You might need many of the other tools that have just been shown. They're all integrated within the IDEs. But my recommendation is to use the newer IDE because it has a much deeper integration into the compiler. You can actually, as you've seen, you can do projects in a folder. You can easily select multiple programmers, automatic updates. 2 years ago or a year ago, we didn't have automatic updates, and it was a nightmare keeping everybody up to date. You can get automatic compiler and error detection, GitHub integration. You can customize it yourself. You've got automatic help, syntax highlighting, and it's based upon Microsoft VS Code, so you get all the tools from there, and you get unified help. Use the new editor. But when you press function key F5 or make hex, whatever which way you choose to compile, you go through what's called the core compiler. And the core compiler is a bit like this. Pick them up here. We take your source code and we do what's called pre-processing. and we pull in the libraries at the same time. They're pulled in automatically, create a contiguous block of code. It goes through a code translator, and that translates all your code into a middleware construct. And so if I'll give you a really good example, if you had multiple line instructions on the same line, the code translator would separate those all out and make sure they're all valid. It will do a lot of translation of all the constants to their real values. And if you want to see a lot of that, we will see some of that. I'll show you that in a moment. It gets passed to the assembler. It then assembles the program for your particular target architecture. Could be an AVR PIC, new AVR, old PIC, new PIC, LGT. The assembler part of the program then assembles up a specific. It produces reports. There are reports being produced. Go and look. There are text files and HTML files. Then it's producing an assembly language specific for your selected chip. It then links that all together and produces an absolute machine code hex file for your particular chip. But it's more flexible than that. That's a simplistic view that most people understand. However, you don't have to use the whole chain. You can actually tell the compiler to go and do something different. At the end of the process, we can change it. We pull in the libraries and your source code through the translator, and at assembly, it produces an assembly language file. It's the same reports, same assembler. We can then pass that out to an external linker. It will then produce a machine hex file. Why would you want to do that? I'll explain. You might want to do that because you want to use and validate the hexadecimal file. You might want to use PICAS or MPASM because you want to validate the assembly. The way to do it is to actually push it through. You might want to put it out to MPLAB IDE to use the simulator. You might want to use different linkers. And there's validation in what I mentioned, GCBASIC. GCBASIC is written and maintained by the team. But if you are concerned, you can always use an external, and I'll show you how to do that. Moving on, there are variants, and the latest builds are there for Linux, BSD, and the Mac, and you can go and do exactly the same thing. However, there's lots of programmers out there in the Linux environment. PIC Plus is a really good one for Linux. And there's an editor. You're going to have to do that yourself. But we do provide you a set of programming scripts. So if you're using Linux and you take the Linux build, there's a set of programming scripts that you can use. They're there for you. You have to compile up the latest build of GCBASIC, and it will just work exactly the same as the Windows. And if it doesn't, let us know on the forum. So what I'm going to do, I'm going to show you a couple of applications when we're in the IDE. We're going to look at preferences, and then we're going to look at code portability. So let's go out to the IDE, clear it up. There's my IDE, it's sitting there waiting for me. There it is, empty. Do I have a program? I open the Explorer. Let's have a look. Do I have? Nope. Because we're looking at, Control J, Control B to tidy up. Let's bring up PICINFO again. Function key F4 gives us a list of all the tools that we've just been previously discussing. If you type in the word PIC, PICINFO, it will come up. It loads in a setup file, and then it pops up the actual window. Let me zoom in on there for you so you can see it. Bring that into focus. I just need to maybe secondary zoom. With that, this is just getting in the picture. Oh, I think we'll go back to. I just need to make it a bit bigger for you, not me. Let me zoom in. There you go. That's a bit better. So I'm going to bring that down to hide the find files because that looked confusing. Right, what can you do in here? So you can go to the preferences editor, which we will do in a moment. You can go to the data sheet, the web page, the errata, the programming guides, if they're available, but definitely the data sheet. If you press that, it will open up the data sheet. On the right here, all the configuration options, and as we've seen, you can copy that configuration by pressing copy, and it will put it in your cut and paste buffer. Chip data. These are all the exposed constants based upon the value that we have that's been determined. So program memory, EEPROM, you might need some of these. And we've shown how you can use some of those parameters. The options tab has the options that are available in the config, all the registers. Not that big for older chips. If you look at the newer ones, huge. All the bits and which register they're aligned to. And then all the interrupts, and we've seen the interrupts. So let's go back to the select chip, select tab, and open up the preferences editor. You can get to this same screen by pressing function key F4 and typing in preferences. Now, programmers. I have been using PICINFo throughout, and it was at the top of my list. And the way I got it to the top of my list was by dragging it. I can drag and drop. I can drag that back to the top. And it says here, maintain power, power on and off. There's many different options in here. All the different programmers. And what you can do, you can actually configure that for your own needs by saying edit. And it says here that the only reason it's going to use this particular programmer is at the top of my list if it's a PIC, P-I-C, a PIC, because it doesn't work if it's an AVR. Let me look at this one. That says PIC as well. Same here. The commands have all been pre-configured for you. Wouldn't go editing those. Uno. Well, if I was using an AVR, it wouldn't use the first two because they were PICs. But it used in this one. It says if it's an AVR and it's not a particular chip family, then it will use that one. And here, you just select your communication port for your AVR programmer. And it's a common port. It goes out through the TTL converter. So you might have to change that. But this is a sequence. It will come through as a sequence. Let's go to the compiler tab. In here, you can see that there's different options. Now, I typically have suppress summary mode, but we're going to look at verbose mode. And you can actually show your GCBASIC source as assembler. So in the assembler program, you can see all that stuff that you typed. Enable advanced variable support. You might need that you'll need that if you're using advanced variables. Remember, they use a lot of memory. So I don't think you're going to get much capability on these old legacy chips. You can create what's called a CDF output file, and that CDF means constant definition file. Constant definition file, and it just lists all the constants that it's found. And you can mute banner messages, and those are the things, little messages that come up during compilation, and then you can treat warnings as errors. Quite interesting. Now, currently I've got PICAS, so I'm going to go back to G. That's how you change from GCASM to PICAS to MPASM. Now, obviously, AVR-ASM isn't applicable because it's not an AVR chip. But let's choose MPASM. Press OK. It's just saving the parameters. I am now going to open up a program. Let me have a look. I think we created one called test, didn't we? Did we create one called test? No. No, we didn't. Let me open up number 10, Hello World. If you remember Hello World, right back at the beginning, it essentially says, define a chip. Let me just move my screen around so you can see it. Define a chip. I've opened up number 10. Define a chip, option explicit. and all it was doing is turning certain LED ports on or off. Let me press function key F5. Let me zoom in so that you can see exactly what I'm seeing on my screen. There we go. Is that the whole of my screen? Is that the? Have I got the top of my screen in? I don't think I have. Let me just resize it slightly. There you go. I'm going to push this little icon at the top, make hex and flash. But when I push that, up pops this little window, and look at all this dialogue we've got. And what was that? We'll have to do it slowly. We're going to have to do that, and it's programmed it, by the way. So let's have a look. I'm going to try and capture what happened. So I'm going to make hex and flash, function key F5, same thing. Make hex and flash. Just going to compile it. It was so fast that I didn't even see it. I think it came up on my other screen. And what it's done, and if we look at this, we raise this little thing here, look, what it did, it's given us a lot more information. It says I'm compiling the full file name, and it says I found that file name as my source. Then it found a set of libraries. Let me move that across. Found a set of libraries. It loaded those libraries. It read the compiler directives to make sure it knew what it was doing. It found the reference file for the chip definition, automatically set it to 32 megahertz. It chose my programmer. It would list them, by the way, as it works its way through. Gives you some parameters around the chip that you might find interesting, and then it goes through what it did. And trust me, there's a lot more debug than this. It then says, this is what I found. I compiled 11 lines of your program. I used one subroutine of 485 that it encountered in all the libraries. But it only used one, so it only compiled one up. Chip resources, program memory, it was 37 words, no RAM, and it's running on the internal oscillator at 32 megahertz. Then it passed it out to an external linker, an assembler, so it passed it out to MPASM. And if you want MPASM, it's up on our website. It then passed the assembler file to it and successfully compiled it. It then downloaded it through my selected programmer using these parameters here. Must be all that lot. And then it said I found it, I erased it, and then I completed it in 9.25 seconds. Most of that, by the way, was programming. We changed the parameters by pressing function. We went through PICINFO, but I'm just going to type in the word pref, edit preferences. It will take me into the preferences editor, exactly where we were before, and I'm going to turn off all that. I don't need to see that. I sort of know what's going on. So it will save it. If someone can work out why it's so slow, let me know. It's open source, you can have a play with it. When it's cleared it down, I'm going to press function key F5 to recompile that very small program, and we'll see the difference in terms of the information provided. There we go. Hello world. Passes it out to MPASM, and it's downloaded it. But look at how limited the information is now. If you don't program it, if you just generate a hexadecimal file, you get very limited information now. But you don't need it because it's just going to work. And if you saw on the screen, it's flashing got MPLAB, okay? MPLABX, okay? Look, it's done it. And that took 1.35 seconds. So let's put it back to GCBASIC. That's the internal one. Press OK. So using an external assembler linker was 1.37 seconds. It takes longer to save the file inside of the ini file. Don't know why it's taking so long. Once it's done that, make the hex 0 seconds. It's a bit faster. Let's press function key F4. Look at the other tool I wanted to show you, AVR-Info. AVR-Info is the AVR version of the PICINFO tool that we looked at previously. Sorry, bit different at the front end because you can't do the configuration. Data sheet access the same. Chip data is the same. I haven't got anything selected quite clearly. There's chip data, the same set of constants. It's a set of AVR masks that you can use, registers, bits, and interrupts. It's almost the same tool, but it's slightly different because there's different. It's a different chip, but you've got the same set of interrupts, the names. You've got all your bits, all your registers, and then there's also a thing called AVR mask that you can use because that's the way AVRs work. And the modern AVRs rely upon these masks. If I go to a legacy AVR, because there's also legacy AVRs like a Mega 8, let's find a Mega 8. Oh, Tiny 10, look, there we go. Its chip data is very small. It has no AVR masks. It has very few registers and very few bits. AVRInfo. Let me go back to my PowerPoint to see what I should have shown you. Code portability. We're going to take a brand new program and we're going to go File, New Text, and get rid of that window there. So we know if we type in #chip, it should tell us what's going on. It won't do that until you save it as a GCB source file. Alt F, save file as, and then give it a file name. I'm going to call it test #chip 16F. Have I saved it as a text file? Look. Naughty boy. Rename. .gcb. Now if I come back into here, Control B, 16 F1937. That's my chip. Option explicit. DI. Oh, here you go. Look, pulse out. We saw that in the pulse out. It's a really quick way of flashing an LED. Port B.5. Port B.5, comma, at 100 milliseconds. So all it will do is compile us up a program that pulses that out. Function key F6 will come, and it's created me a hexadecimal file for a 16F1939. I've got 1937 installed, but that's not the point here. Watch this. Mega 328P. I am changing the chip architecture completely. Code portability. Function key F6 to generate the hexadecimal file. That is a hexadecimal file generated for a Mega, and it will work. We can load that in, and it will work. #chip LGT, completely different architecture. Function key F6 to generate a hexadecimal file, and it will work. 18F2250. Oh, I pressed function key F6, so it's oh, I got the name wrong, haven't I? Look. Function key F6 to generate a hexadecimal file, and it's created one for an 18F. This is code portability. Now, you'll get code portability to the greater extent when you're using the public commands. But if you start using things like interrupts, then you just need to make sure that you're aware that the interrupt name may change and the interrupt vector may change across chips. But in terms of generalization of code, it works well. So you can compile code up for a 16F, 10F. I'm trying to think. Port B5, if it doesn't exist, if I go for a 10F, trying to think of a smaller chip. I never get to remember these names. 10F, 202, 204, function key F6. The B5 may not exist. Oh, it says port B not explicitly declared. That tells you quite clearly that there's an error on that line and that doesn't exist. It probably doesn't have port A in actual fact, okay? It's probably some other name that I would have to go and check in PICINFO. There you go. I think it might be something different. So why don't I look in PICINFO? I'll drag that into our view. Type in 10F. Was it 202 I chose? Have a little peek at my code. 10F204. The register names. Oh, GPIO. There you go. Look. GPIO is the name. There's a name here. I've actually got names in here as well. Look. GPIO. GP0. There you go. I don't use these old chips like that. Function key F6 to compile that. It's compiled it. Code portability. So I hope you've enjoyed that work through the toolchain and code portability. The next video is on assembly, alternative assemblers and MPLAB. So we're going to look at those in detail, specifically looking at using PICAS and a simulator inside of MPLAB-X. I'll just pull up the full screen so you can see that. Part 18. Enjoy.